At the core of every digital system, the abstract concept of counting must be translated into physical hardware logic. Physically, a digital counter is a sequential circuit built from two distinct elements. First is the state register, which temporarily stores the current numerical value. Second is the combinational incrementer, which calculates the next sequential value based on that current state and feeds it right back to the input. This entire loop is governed by a synchronous clock signal. The register updates its state strictly on the rising edge of the clock pulse. Today, engineers do not manually route these individual logic gates. We use behavioral-level modeling in Verilog to describe the function we want. By building a basic reset counter, expanding it to a presettable up-down counter, and applying it as a frequency divider, we can see exactly how Verilog syntax dictates the final physical hardware. This schematic shows our baseline architecture, a 4-bit counter with a synchronous reset capability. Physical hardware must evaluate its inputs simultaneously at specific recurring moments in time. The always block tied to the positive edge of the clock enforces that state changes only happen exactly when that rising edge occurs. Before the counter can count, it needs to know if it should be resetting. We have to prioritize the reset command over the standard increment operation. In Verilog, we establish priority through the order of execution, starting with an if reset statement. If the reset signal is active, the counter ignores all other logic and forces the output to 0. If the reset is low, the hardware moves to the default counting behavior. We use a non-blocking assignment, meaning the register takes its current value, adds 1, and prepares to store it on the next clock edge. By structuring this as an if-else statement, the synthesis tool infers that it needs to insert a multiplexer, hardwiring the reset path to take priority over the incrementer path. Real-world applications require far more complex, multi-function control over the counting sequence. We add 4 new control inputs: clear, load, enable, and an up-down direction toggle. This creates a hardware conflict. What happens if the system simultaneously receives commands to clear, load a new value, and count up? We must define a strict hierarchy. Clear dominates load, and load dominates enable. We use vector concatenation to group these competing control signals into a single clean 3-bit bus. To resolve this specific priority vector, we use the case X statement. Case X evaluates conditions from top to bottom, stopping the moment it finds a true match. The highest priority state is clear, represented by a 1 in the first bit position. The X syntax denotes a don't care condition. If clear is high, the hardware entirely ignores the states of the load and enable pins. The secondary priority is load, represented by a 1 in the second bit. The counting logic is bypassed, and the external data state is loaded. The final operational state is enable. The first 2 bits are 0, and the enable bit is 1, permitting the count. Notice the ternary operator here. It checks the up-down variable and dictates the counting direction without requiring another bulky if-else branch. The case X approach prevents the compiler from generating deep, inefficient logic trees. The result is a faster, optimized hardware implementation for complex hierarchies. Counters are not strictly for numerical sequencing. They are frequently used as temporal bridges between different hardware domains. This diagram shows a common engineering problem. A central processor running on a dense 50 MHz clock needs to interface with a peripheral requiring a slow 1 MHz clock. The 50 MHz signal completes 50 million cycles per second. That means exactly 250,000 fast pulses occur in just half the period of the slow 1 MHz signal. We set up an internal counting variable, n, tasked specifically with tracking these high-speed pulses. As long as n is less than 250,000, the counter increments and the output clock state remains frozen. The trigger event occurs the moment n hits the threshold. The counter must immediately reset to 0 to begin timing the next phase. Simultaneously, the output clock signal is inverted using the bitwise NOT operator. In this context, the counter calculates time, synchronizing high-speed logic with slower downstream components. Behavioral Verilog is precise, but designers easily fall into the trap of assuming physical hardware behaves as perfectly as the simulation implies. The danger is clock domain crossing, when a counter's output is read by a system running on an entirely separate asynchronous clock. This simulation waveform displays an ideal binary counter. The transitions from 3 to 4 or 7 to 0 occur instantly. If an asynchronous receiving clock samples the data during this microscopic transition window, it will read transient garbage states instead of the correct value. This chart shows the industry-standard hardware solution, gray code counters. In gray code, moving from any number to the next only ever requires exactly one physical bit to change state. With only one bit changing, an asynchronous clock can safely sample the bus without ever catching an intermediate garbage state. Mastering digital design requires looking past the code. You must understand Verilog as a literal blueprint governing the strict physical constraints of hardware logic.